Okay, let's get ready to talk about inverses, section 1.6. So if we have a function and that function, we flip them over the line y equals x, which is of course that diagonal line, right? Y equals x, y-intercept of 0 and a slope of 1. It's going to look like this. You will get the inverse of whatever function you have. So it's not quite that easy. There's one more restriction. Let's see if this big green box will tell you. Yes, not all graphs have inverses. Graphs that have inverses have to have one-to-one correspondence, which means that for every x, there's only one y, and for every y, there's only one x. So would this graph have one-to-one correspondence? So let's see. For every x, there's only one y. Well, let's see. When x is 1, there's only one y. When x is 2, there's only one. That's right. So that's true. For every x, there's only one y, and we know that's true because this is a function. But one-to-one correspondence goes beyond being a function, and for every y, there's only one x. And this one's not going to be true, right? When y is equal to 3, that aligns with two x's. That aligns with the 0 and 2. So this does not exist. So that means it doesn't have one-to-one correspondence. There's a quick way to see if the graph of a function has one-to-one correspondence. Let's see if one of these blocks tells me, oh, there we go. An easy way to tell if a graph has one-to-one correspondence is with the horizontal line test. So if you imagine just drawing a horizontal line through a function, if the horizontal line touches a function in more than one place, then one-to-one correspondence doesn't exist, and therefore the function would not have an inverse. So I'm sure we're hoping that we see stuff like that in our homework, because we just say, nope, there's no inverse, I don't have to find it. Let's move on here. Nothing to see here. Let's see what's behind this block. Okay, inverses, when we have a function that has one-to-one correspondence, and we know that it has an inverse, their tables are going to look really interesting. Let's say for this function here, f of x, that when x is equal to -2, y is equal to -6, its inverse is going to have the opposite thing happen. Instead of the y being -6, it's the x being -6. The whole table flips. So I'm not telling you anything new. I know that you did this in Algebra 2 Trig last year, but this is just a good reminder. Here are some examples of functions and their inverses. So the function is in blue. The inverse is in red. Well, I think for all of them, actually. And the line y equals x, sometimes the green dotted and sometimes the black dotted. But this is just examples of what a function and its inverse would look like. I like to think of it like this. If looking at this first picture, if I took my function and I took a really smeary blue marker like that, and then I took the paper and I folded it over on the, I folded it at the y equals x line right here, and I, squished my paper up, not squished it up, but you know what I mean, pressed down on it and rubbed it, then what I would have remaining is that second, I don't know why I'm making it dotted, because it's not, it should be solid, that's its inverse. All right, so we know what inverse graphs look like, right? We can start out with a function that has one-to-one correspondence as well as being a function. So we know that what an inverse of that function would look like. We also just touched on real quickly, let's get that back out. We know what tables would look like for a function and its inverse. They're going to be flipped, right? Let's see, what about equations? So here, example 1 says, if we have a function, x plus 2, then the inverse of that function will be, all right, I guess we have some choices here. We could go ahead and graph it and then do that smeary marker and fold it over on the y equals x line to see, but we're not going to do that because we're dealing with equations. So we're going to remind ourselves, wait a minute, let's look back at the table. When we were looking at the table, we noticed that for the function that we were given, the x values and the y values are such that when we look at the inverse, those are flipped, right? The x values become the y values, and the y values become the x values. So that gives us the hint of what to do with an equation. So what I'm going to do is remind myself, of course, that f of x is equal to y. So I'm going to flip. If I want to find my inverse, I'm going to flip the values of x and y. So that means for my inverse, I'm going to have x equals y plus 2. And I'm not done because we like our functions to start with y equals. So we're going to go ahead and isolate y. We'll subtract 2 from both sides, and then we'll make it look pretty. I just like my y on the left side. Here we go. Y equals x minus 2 is the inverse of the function. Y equals, I'm sorry, did I say x plus 2? Y equals x minus 2 is the inverse of the function. Y equals x plus 2. Okay, easy enough. Determine if the function 2x and the function x over 2 are inverses. So what we can do is we can just start with the function that they gave me and find the inverse, right? We can switch the x and y values and then solve for y. And yep, that looks like that's the same as that. So yes, they are inverses. I don't know if I needed to make this tutorial. I think you guys probably remember this. It's pretty basic. Find the inverse. Oh, okay. Now we look at something that might take a little bit more time and thought. So I'm going to change f of x to y. I'm going to change that. That's a cubed root of x minus 5. I'm going to then switch my values. I'm going to replace y with an x and my x with a y. And I'm going to go ahead, to isolate my y, I need to get it out of that cubed root. So the only way to do that is to get rid of the cubed root by cubing both sides. So we'll have x cubed equals y minus 5. I'm almost there. I'm going to add 5 to both sides. And I get that my inverse is equal to x cubed plus 5. Okay, we're going to continue to find the inverse of this function. So we'll go ahead and switch out. I'm going to remind myself that g of x is another way to say y. Then I'll go ahead and switch them. The y becomes the x and the x becomes the y. And what I'm going to do is I'm going to multiply both sides. I need to get the y's together before I can isolate them. So I'm going to multiply both sides by y plus 2. So I can get the y plus 2 out of the denominator. So I'll distribute my x. And of course the y plus 2's cancel out. That's why I multiply. I'm going to get my y's on one side and my x's on the other. I'm going to go ahead and subtract the y. All right, I wanted to do 2 steps in one, but I won't. And then I want to get just the terms with the y in it on the left. So I'm going to subtract the 2x from both sides. And I want to isolate the y. The only way to do that is to factor out the y from both terms. Almost done. I'm going to divide both sides by x minus 1. And there I have it. Can I do anything if I factor out a negative 2 from the top? Does that help me? Nope, that would give me x plus 1, so I'm done. There is my inverse. If I sound tired, it's because I am making this tutorial at the very end of the school year of 2017, and students wipe me out by the end of the year. Love them, but yes, it is exhausting for all of us, isn't it? So you're watching this hopefully in the beginning of the year, and we are into a great beginning of the school year. Thanks for joining me, and I'll see you in class.